Hi everyone, my name is Hanson. I'm from Cluster 3, which is the best cluster at Cosmos. Now I'm going to do my people on Couchy and Magnus, which are two really influential people. And did I mention that I'm from C3? That's cluster. Okay, so my first person is Augustin Louis Couchy. He was born on 1789, died on 1857, so he lived a good life. He was really smart, he graduated with the highest honors, and he was really famous for all his proofs. One of his proofs he did when he was young is he gave a really good solution to the problem of Apollonius, which is basically you're given three circles and you're trying to draw as many circles that are tangent to all three of the circles as possible. Another one of his famous proofs is his proof to Euler's polyhedral formula, which states that for basically every polyhedra, the number of vertices minus the number of the edges plus the number of faces in the polyhedra always equals 2. He did this by flattening out the polyhedra, let's take a cube, and then he drew lines in between them and created triangles for all of the cube's faces. Note that this does not violate the initial condition because each time he drew a line, he adds a vertice, but he also adds an edge, and 1 minus 1 is 0. And after that, he removed the triangles. Note that this also does not disrupt Euler's formula because every time you remove the triangle, he takes away a vertice and an edge, which also gives a net value of 0. And then he finally removed triangles until there was only one triangle left, which has 3 vertices, 3 edges, and 2 faces, which all will equal 2. Plug them into the formula. And this shows his brilliance because a person, no person can't do this. He also founded the theory of stress, which basically states that in any given uniform material, each particle in that material will pull on the particles around them to basically talk about the internalization of force. And with this new theory of stress, he created his stress tensor, which consists of a 3 by 3 matrix that would be able to determine the stress within any point within a given material, like this cube over here. And his most famous achievement is he created he more or less found a new branch of mathematics, which which has complex numbers in them. And this is really famous because it's really important and you can do a lot more stuff with it. He was also the first to really promote rigorous analysis, both in his research and in his teaching lectures. And basically allows you to find basically gives Couchy in his life was a really rigorous writer. He writes lots of papers. He is number 2 for most papers written, while Euler holds the first place. He was also a really bad teacher because yeah, it's just that. My second person is Magnus. He was born in Berlin. He wanted to be a chemist where he grew up, but he switched to physics in his later life. And all of his research and contributions is in the field of physics rather than in chemistry. And unlike Couchy, Magnus was known for being a really great teacher. He had a state-of-the-art lab in his class in which he did experiments to further explain his lessons in a way lectures could never do. And he did his job really well. Lots of people were really intrigued by his experiments. And many great physicists came out of his classroom, like my man Claudius, Helmholtz, and Weizmann, and lots more famous people. And he also created the Magnus effect, which basically stated that spinning balls curve in the air, and the direction of the curve depends on the direction of the spin of the ball. And let's take the example of a backward spinning ball. For example, imagine a backward spinning ball in the air. It will push the air in front of it, above it, and behind it in a downwards angle. And this will allow this will generate lift up. The downward angle of the wind going behind the ball will generate lift up the ball. Because of Newton's third law of action and reaction, the ball pushes the wind down, and therefore the wind lifts the ball up. And that lift is called the Magnus force. And the Magnus force is defined as rho of the air times the velocity of the air times the vector force g created by the ball, in which g equals 2 pi times the angular velocity of the ball times the radius of the ball squared. And Magnus effect has lots of real-world uses, and it is commonly used in sports that are heavily involved in balls, like ping pong. Players would want want to spin on the ball to change the arc of it when it's in the air, because it can do that. Magnus is also famous for his green salt. Like, he founded his green salt, which is the first platinum amine compound discovered. And this is really cool because it has a one-dimensional structure, which is really interesting. And yeah. And my topic is stability of ignition and mass flow rate. And again, I'm still Hanson, and I'm still from Cincinnati. I know I miss all you guys like afterwards. You guys are all like great and stuff. And Cosmo's the best. The mass flow rate is defined as the amount of mass of a material that goes through an area over a period of time, or basically mass over time. And it is calculated in units of kilograms per second. This is the formula for mass flow rate. And, well, that looks really bad, but mass could also be defined as the density of an object times the volume of it. And this is really freaky, but like mass flow rate could also be defined as the so you can commonly see mass flow rate is used in hydrodynamics because the mass flow rate at any 2 points in a given system will always be the same because of the conservation of mass. You can't have more mass and you can't have less mass, so mass flow rate will always be the same. You can also see in electricity a current, and because the rate of flow change in a circuit is called a current, and it is measured in amps or coulombs over second. But like, mass flow rate is really interesting and cool because you can use it to calculate like masses that are constantly changing, and you can't use Newton's second law for it because the mass is changing. For example, like you can use mass flow rate for rockets because the mass of a rocket is constantly changing. So there's this diagram of a rocket, for example, that utilizes the conservation of a momentum to like send the exhaust fuel backwards in order for it to push the body of the rocket forward. And that's the mass flow rate in the equation. And you can, and like everything is really like weird. I don't know why, but like it's really messy. I don't know at all. But it's like mass flow rate is related with the change of the velocity of the rocket. This is Tchaikovsky rocket equation. Basically connects the change of rate of velocity to the speed of the rocket fuel rocket exhaust fuel that leaves the nozzle of the rocket. And like you want to maximize the velocity of the fuel in order to like send the rocket, like make the rocket go as fast as possible. And you can use it by choking, which increases the area over here to like increase the velocity of the exhaust fuel going outward. And you can also use the Venturi effect to further increase the velocity of the fuel by also lowering the pressure of the fuel. This, along with choking, allows rocket gas to have as much velocity as possible, because if you lower the temperature and pressure of the fluid, then the velocity will go like really high because mass flow rate. So, and rockets utilize this a lot to go as fast as possible. And now for stability of ignition. So basically when a system undergoes a chemical reaction, like that involves heat, heat is transferred and released. And when heat input equals heat output in the system, then the system is in equilibrium. And there are two types of equilibrium for like both heat and mass, which is stable and unstable. In a stable equilibrium, if you disturb the system, then the system will go back to equilibrium. But if it's unstable, then it will not go back to equilibrium. Like, let's look at the example of a pendulum, so a simple pendulum. If you disturb the pendulum, then like it will bob back and forth, but eventually just go back to its equilibrium state. And like if you disturb it some more, it would just go back to the equilibrium state. And this for unstable equilibrium, let's take the example of a ball on top of a mountain or a mound. At that moment, the ball is in equilibrium, but if you disturb it even a little bit, it will just like go out and just like drop, and it will not come back to equilibrium state. And now this stability of ignition applies heavily to rockets. Let's look at this rate of change of temperature formula. Like it appears to be really ugly, but like a lot of it is just constant. At its core, this formula is the rate of the temperature of time versus the temperature of the rocket. And if you graph it, like, this is parabolic function, but like, pretend it's an E function because I can't find it on the images. So in this graph, there are 2 points of stability. There's 2 points of equilibrium. One is stable and one is unstable. And if the rocket temperature goes too far that way, then the rate of change of the temperature will become too high, and it will just go out of control and it will explode. Rockets rarely explode due to instability because the amount of heat that must be added in order to go past the second equilibrium point is just way too high to be like achieved ever. Well, not ever.